Hey everybody, how's it going? I hope you're doing well today. So this video is on train, test, and validation sets, a very important concept in machine learning, and if you do not know it already, I highly recommend you stick around and watch this, because no matter what your skill level is, whether you're just touching machine learning, you just Googled these terms, or you just ran into this, it is going to be a really helpful video for you. So the main idea that's important for now, to run a machine learning model, it needs to be trained on data. And we also don't need to just train that model, we need to evaluate it on data to know that it's actually going to perform well. So we definitely have two splits or partitions of a big data set. We definitely split it into a training set where we train the model on that data and then we test it and evaluate that. But in this video, I'm going to show you why you actually need a third split of the data, but we're not there yet. For now, we're going to assume just that approach of train and test, and we're going to run into a problem. We're going to see why we need that third split. So the data set that we're going to use is California housing, and you can see that there is test and train here. We'll train on this and we'll test on this for now. So df train, we'll call it, is equal to pd.read CSV of sample data / California housing train.csv. Okay, and then df train.head is going to be not defined because we didn't import pandas. Good start, me. So import pandas as pd, and df train, that is our data frame. And we can also load in the test data frame very easily with df test is equal to pd.read CSV of sample data / California, sorry for this annoying part at the beginning, California housing test.csv. And we should see df test got confused there. Head is like that. Okay, so this is the first 5 rows of our training data set, and these are the first 5 rows of our testing data sets. And each of the rows of information are all of this longitude, latitude, housing median age, total rooms for some area in California. So it has some location. It has some information about housing and rooms. And the final thing, which we're going to try and make a machine learning model for, is the median house value. Now, I have a full project on this that goes through everything on how to do this well, but we are going to focus a much smaller condensed video on the reason and how to do it, train, test, and validation sets. So for our purposes, we are going to just stick to a model or a group of models that use 2 variables to predict. We're going to use the housing median age and the population, so housing median age and population, to try and predict the median house value. We're assuming there's some sort of pattern where you can use these variables, housing median age and population, to try and predict this continuous value. So this is called a regression problem. We're predicting a continuous value of the median house value. Now, since I said we needed those variables, let's go ahead and do df train2, I guess, is equal to just df train, where we specify we want those particular columns, which is housing median age as well as population. And the final one is median, is it house or housing? Median house value. Okay, so we'll do that and show that the head, the top 5 rows, is actually, well, there, I forgot to do head, but we have 17,000 rows total. That's actually important to know, and 3 columns. Okay, and just to show the head is right there. Okay, so we will do, again, kind of a boring thing for now, but the exact same thing, but we are going to switch that to test because we're going to need that. That'll be test, that will be test, and that will be test. And there we go. Okay, so now that we've got that, let's go ahead and make our first machine learning model on the training set and then evaluate it on the test set. So we do this generally with converting stuff to NumPy. We don't have to use too much NumPy, so don't worry about it. But we do need to convert them to the data frames to NumPy arrays. So train df to NumPy is going to be train df to NumPy. That's all you have to do. So that converts that whole thing to this big NumPy matrix. And then we will take particular columns for x, which is going to be our mark our input, and our output is going to be this y train thing. So how these models all work is through supervised learning. We feed it many input-output pairs. The input is going to be, one input is this and that, and the output is going to be that. So this is setting up our input and output arrays, where x is this whole matrix of inputs, and y is this big long vector of outputs. Okay, so xtrain and y train is equal to train df2 numpy, big long name. That's going to be, we need to subset of this so we get all of the rows and then the first two columns, and I can do it like this, where I'm basically saying all the columns from the beginning, not the last one. And then train the same thing, train df2 numpy, where we get all the rows and then just the last column like that. Okay, and then we can check their shape, which says how basically the arrangement of the items, and I'll explain that. Where train df2 numpy, train df2 does not exist. I must have called it something else. Yes, this should be df train 2, 2, yeah, 2. Okay, so 17,000 rows and 2 columns and 17,000 rows. So that here, this is our matrix of input, and this is our vector, corresponding vector of outputs. We can use this to fit a linear model with from scikit-learn.linear model. Import a linear regression. This is just the base linear regression, which is going to draw a line through data. We will do from scikit-learn.metrics. We'll import the mean absolute error. So that linear model, by the way, mean absolute error is basically just a different measurement. Normally we use the average sum of squared errors, the mean squared error, but for interpreting this, we're going to be using the mean absolute error, which is just really on average how far off is our guess, or how far off is our model from the actual true answer. So we're going to fit our model, or train it, with linear model is equal to this linear regression object, bracket bracket dot fit, and we just need to pass the input output pairs with x train and y train. Okay, and then linear train predictions. So we're going to get the predictions for that training. This fit the model. We'll get the predictions for corresponding to the inputs, and it's kind of weird because this fit probably made those, but we're just going to get the predictions again, and we'll see what these are by calling linear model. That's con linear model.predict on x train, so get all of our corresponding predictions, and then we can check how far our predictions are with mean absolute error, comparing the linear train preds, the predictions, to the actual training data. So this is going to show us the error on our model for the training data, and we don't really care too much. We care that our model, it can perform well on unseen data. So what we have here, sure, we have this mean absolute error, which is 91,000, and it's not too bad given that these values are so big. We're off on average by $91,000 in the training set, not a big deal. But we don't really care ever how, at least not for machine learning type problems, about the error on the training set. We care about the error on some data set that is used that hasn't been seen before. Seen being, this is seen right here. We're fitting it by training it on this data. We want to see how well our model can do on unseen data that the model hasn't been trained with. So to do this, okay, we have this test split. So we can get something very similar. It's going to look basically the same thing as this, where we can copy this, and this, I believe I called this test df2 numpy is df test2, I hope, or df test. Let me see what I called that. Yep, that's df test2 to numpy. X train, this is going to be x test, and y test is test and test, and finally test and test, a lot of tests. Okay, so that is now 3,000 by 2 and 3,000, meaning we have 3,000 rows and 2 columns and 3,000 corresponding outputs. Okay, same shapes except we have less training examples, or less examples. So let's check how well our linear model did on this test set. That's of interest to us. So let's do mean absolute error on the y test. Actually, I have it in a different order. I'll just try to stay consistent with the order, but it doesn't really matter. With linear test preds, which I haven't made yet, we're about to make this, linear test preds and y test. And we can get this, we can get linear test preds is equal to linear model dot predict on the x test. Okay, and then we see this is a little bit weird to start off with, because generally your error for the unseen data is generally higher. It should be higher than it was in the training set, because basically your model is learning to fit this data on this data set, and then we check the error. It should be lower, and we should have less error than we do on some data set that we haven't seen before. But that's what it happened to be, and sometimes that happens. So anyways, we have some error here, and we have some benchmark to beat, which basically we want to train other models and see, we want the best model. Or I'm not going to show you how to make the best model, but I'll show you the process of how you would go about making the best model with this train, test, and validation, well, soon validation, right now train, test idea. So if we're to make another model, let's suppose we could do a random forest. So from scikit-learn.ensemble, we will import random forest regressor. And we'll say rf, just our random forest variable, is equal to the random forest regressor with just the default by now, for now. If you guys happen to know off by hand, we can tweak this random forest by its number of trees, which is called n estimators, and its and its max depth, so how big these trees are basically. But we're just going to stick with the default parameters for now. We'll tweak them later, and we'll do .fit. We're going to call it in the exact same way, .fit with x train and y train. Okay, and then after that we can just go ahead and get the training predictions and the test predictions with rf train preds is equal to rf.predict on x train, as well as rf test preds is equal to rf.predict with x test. Okay, so now that we have those, we can check the error. I'll just show the error before I split it out here into here's train error, here's test error. We're going to do it both at the exact same time by just copying this in, and we have mean absolute error on not linear test preds, but rf train preds with y train, as well as the same thing, comma, mean absolute error on rf test preds and y test. Okay, so here's the error of our just base random forest on both the training set and the test set. It is 42,000 instead of 91,000, so that's way better. But we don't care about how it does in the training set. 98,000 on a test set compared to 89,000. So this did worse. Okay, we didn't like this. Let's try and tweak these things. So the way you tweak this is I can change, say, n estimators. Maybe I can make this 10. Okay, and then I can also change max depth. I'll change that to be equal to maybe 5. I don't know. Run that again. I'm just going to monitor this value for the most part. It's an interesting discussion to look at the difference between these two. But for the most part, I just care about the error on this test set. So 87,700. Immediately, I already, just by tweaking those a bit, I got better, a lower error than the linear model did. So I played around with this, and I got a better model. Now, I could repeat this process and keep trying to get better and better. You know, maybe I can try 12 and 6. Did that go down? No, it seemed to have gone up a little bit, so I'll just undo that. And no matter what, I'm playing around, and you can change. You could try more variables. You could do different transformations. You could play different algorithms, like a bunch of different algorithms, like gradient boosting or TensorFlow neural network models, whatever you wanted to do to try and get this number down. Now, we've picked some model based off of getting the lowest test error that we could possibly get. That's great. What we want to do is now put this into production, or we're happy with our model, and we also want to say, hey, boss, or whoever we made this for, if it's ourselves, whatever, we want to have a valid estimate of how poorly this thing is going to do, how much error it's going to have. That's important to us. Now, what we could say is, on average, we think it's going to be off by 87,799, or we could use this value, 88,791. And those are reasonable estimates, but they're not nearly as good as what we could have gotten if we had another test data set. So basically, what we'd like to do is we trained this model on this data set. Great. We've lowered this other error down over and over again on this test set here, except now what we want to do is introduce a third data set that hasn't been seen at all in this process. We haven't been training on it. We haven't been trying to lower it. It has just been called basically a holdout set, another data set where now we can say what is actually the error of our model. And so that is the only data set that can do that accurately. And so we're going to keep that. Now, generally what you're actually given is just one big data set. For us, we happen to have train and test, but that's not usually the case. Usually you just have this big data set and it's up to you to how to partition it. And so generally the split of the data is kind of, shuffle it randomly. And then you would get, say, 70% for train, 15% for validation, 15% for that final test, sometimes called holdout set. Validation is also sometimes called dev or development set, by the way. But I'm going to use train, validation, and test all the time. And yeah, so that the split is up to you, but no matter what, you're going to be doing some sort of train test split function. So this is called from scikit-learn.model selection. We import train test split. Okay, this is just a function that partitions both the inputs and outputs, and I'll show you how to call it like this. Train test split of, we're going to give it, for us, it splits whatever you give it. So we're going to give it test, and so we're going to split our test data. And I know I'm using it interchangeably, it's kind of weird, but our particular test set, we're going to split that into validation and test. Okay, so train test split, we call that with x test as well as y test. And then you can kind of specify this parameter, and not just kind of, you can definitely specify this parameter that says basically the split, so how much you want to split, but we're just going to do 0.5, so we'll do test size is equal to 0.5, and then what this thing returns is it's this organization. Honestly, I always forget. Sometimes I implement my own train test split function, but you can do, it's going to be xval for us, xval, and then it's going to be x. I'll call it holdout so that, or just hold so that it's not confusing with the test, but how I was calling test before with this third split of the data set, that's what I'm going to call here. It's called holdout because basically you keep it until the very, very end. So x hold, and then it's going to be the y's, so y val and y hold as well. And you could feel free to call this test, or sorry, feel free to call hold test if you wanted to instead. Okay, so we split that up, and then we should see, if I change this to all of its shapes instead, we see xval.shape. I'll just copy it like that. xval.shape, hold.shape, yval.shape, and yhold.shape. We can see it split up that 3,000 rows, so the 3,000 by 2 into 1,500 by 2 and 1,500 by 2, and these are 1,500. Okay, so hopefully that made sense. That was the main part of this video to understand that for sure. And now just to show you how you do it to finish off our project here, we would get, so maybe, okay, so what we would have done from the beginning is train models on the training set, and then evaluate their performance on the validation set, try to lower that, and then we pick one and say, actually check its error on the test set. So let's do that quickly. We've already trained the models, so we're very happy. We're fine with the trained models that we have. But what I can do is get linear validation predictions is linear model dot predict on xval. Okay, and I can get the error on the training set as well as the validation. I'm not going to look at the error on the test set quite yet, or the holdout set. But I'm going to say mean absolute error on, it's going to be, I'll pass it yval as well as linear val preds. Okay, so that's going to be on the validation. And I guess I'll look at it on the test set as well. So the second one will be for validation. This again, I will say, we've already looked at this value. This should be exactly the same, but I just want to show it as well. Okay, so we make a linear model. This is how well it did on the validation accuracy. Interesting. Now let's copy this and then make it for the random forest model. And if you want, again, we're basically saying we're started from scratch here. We are using the same trained models, but I'm saying that if you were to actually do what you were supposed to do, go ahead and make whatever kind of models that you want to right now and sit here comparing the validation accuracy or error. We want us to get the lowest of this no matter what. So linear val is going to be converted to, this is going to be RF val preds, and this will be rf.predict on xval. That stays the same. Get the y train and linear, this will be converted to rf train preds, and this last one will be RF valpreds. Okay, so here we have an error of 88,000 on the validation set. Okay, so it is lower. We could do whatever we wanted to try and get this to be lower. We pick a model. The model that we're happy to be picking is just, for simplicity, going to be the same random forest. It had the lowest validation. Okay, and now, actually, just to really prove that point of what we're trying to do here, we got 88,207. Let's quickly try to beat it. And so if we go up here to, sorry for the headache, maybe we go to this, okay? Change this to 11, and just for fun. So here, we are trying to beat 88,207. And here, we get, if I train that, don't worry about these measurements right here, 88,207, this error went up, okay? We weren't as happy with that. We were going to stick with that other parameter of 10, and don't worry about that. It goes back to what it was before. Sure, we're happy with this, we'll pick that model. So now we've picked a model, we are just going to look at the test or holdout error for our final model here. So we're gonna copy basically this whole thing here. We're gonna say RF, I'll say hold or test preds. RF holdout preds is going to be this rf.predict on x hold, that third split of the data, and then mean absolute error on y test, except it's actually y hold. So on y hold, and then RF holdout predictions like that. And we can see that the error, we can report back and say, hey, our error is actually 87,000. Now, and I know it's kind of weird that before I said this was probably overly optimistic. This happened to be, this was 88,000. And this is 87,000, whatever. Usually it's higher on the final model that you pick. It doesn't always work out that way, but that is how you give an accurate estimate of your model. Now, it's worth noting that there is this other concept called cross-validation, which is very similar, but a more elaborate method to, in general, produce a better model than what this would produce. But that's not always feasible. So cross-validation, which we'll see, is very inexpensive operation. And it's if you have a big data set, it's something that's hard to do, as well as a big model and trying to tune all these parameters. It's not always a feasible thing to do. So this is a very common practice for sure. The train and test, just train and test, those two splits isn't really commonly used. Generally, we at least do train, test, and validation sets, and sometimes we do this idea called cross-validation, which I'll explain pretty shortly in another video. So if you like this, please drop a like. If you're not subscribed, make sure you do that. And yeah, I'll see you soon.